So let's start the last two talk this wonderful conference. So it's my pleasure to introduce Zoe Chatzidakis from CNR and Economosphere. And she'll talk about definable Galois theory in difference field.
Thank you. Thank you. I thank the organizer for having invited me here. It's the first time I come to a DART meeting and didn't have the opportunity to then. Now, it's very nice to be here. It's very interesting stuff. Okay. So I'm going to tell you a few things about difference algebra. Okay. So this is joint work with Udi Hrushevsky. It has been joint. I mean, it has been. How do you say? It's not yet written, but it should be written at some point. So, as I said, I'm working in difference algebra. I'm working inside a large, existentially closed difference field U. So, a difference field is a field with a distinguished automorphism. To be existentially closed just means that any finite system of difference equations which has a solution in a field extension of U has a solution in U. Now, because we want to work in a large one, I'm actually going to strengthen these conditions to have to look at arbitrary systems of difference equations, so infinite but of size smaller than the size of U. So model theory, so this doesn't matter, I mean, this has no importance in terms of what the elementary theory of the difference field U will be. In other words, what are, and the behavior of, sets and interactions between sets. So by which I mean you take your favorite set of solution to difference equation and you take another one, are there any relations between the two? So will be affected by the fact that my U is large. If something happens, then it will happen in any existentially closed difference field. Model theoretically, so they are very nice structures. Their theory is super simple. We know the elementary invariants, and we know lots of things about them. The algebraists actually hate them because the fixed field is not algebraically closed. So that to them is totally ready-bit done. How can you do something with a fixed field which is not algebraically closed? So the fixed field is pseudo-finite. So in a sense, it's not algebraically closed, but it has very nice properties. The Galois group is generated by, the absolute Galois group of these fields is generated by sigma, not surprisingly so. So what's the reason why is the fixed field not algebraically closed? It's simply because the equation sigma square of x equals x and sigma of x different from x. Okay, so that's not an equation, but can be made into an equation with two variables. This cannot have a solution in a field where the fixed field is algebraically closed. Right? Okay. The other thing they don't like about this is that there is no real concept of difference closure. While every difference field embeds into an existentially closed one, there is no small as such. And the reason is that, for instance, if you look at Q, let's say, Q, where sigma is the identity, you need to extend sigma to the algebraic closure of Q. So there are 2 to the LF0 way of extending it. So obviously there is no prime model. Okay, so this is, I'm here cheating because you could think, okay, the behavior of sigma on the algebraic closure of Q should be, in the same way as you specify the characteristic, you should be able to specify this. But there are other examples where you can fabricate equations where, you have this difference equation should have a solution, but however, there are 2 to the LF0 ways of realizing this thing because you don't know, you need to explain what the behavior of sigma on the algebraic closure of a solution is. Okay, that's the problem. So there is no good notion of difference closure. That's another reason why algebraists don't like it. I think these are all the wrong reasons. Still, I think, you know...
Reasons to not like it?
What?
You mean there are better reasons to not like it?
No, I mean, you should like them. I mean, I guess, you know, everything which happens at the quantifier-free level actually does not really depend on the ambient model U. I mean, it's... So, throughout, I fix an existentially closed difference field, as I said, large. Everything is going to be happening inside. I have a smaller algebraically closed difference subfield K. You have a finite tuple in U, and so I'm first going to explain what I mean by QF internality to fixed sigma. So we say that A over K is internal to fixed sigma if you can find a difference subfield E of U, which contains K, of course, and is linearly disjoint from the difference subfield generated by A over K from over K. Yes, linearly disjoint over K, right, obviously. And a tuple B in fixed sigma such that E of A sigma is equal to E of B. Okay, so the difference field generated by A over E is actually the same as the difference field generated by the tuple B, and the tuple B satisfies sigma of B equals B. Right. So these are what I call internal elements which are internal to the fixed field. So if you think about, so another way of saying it is that if you look at the set of difference equations, if you look at X, the set of difference equations over K, which are satisfied by A, then there is a birational difference map between this set X and the fixed sigma points of some variety Y defined over fixed sigma. Now the birational map, so it's defined by difference polynomials, it's not everywhere defined, and it's defined over something which is bigger than K, it's defined over this E. Actually, this E can be taken as generated by a set of solutions of this set of equations, so it doesn't really so much depend on the ambient U, it really depends on A and K. Okay. Right, and when you have a set which is defined by equations, the equations, well, you say it's internal if and only if all its elements are internal. Examples. First of all, I mean, you all know these examples actually, but you don't know that you know them. So you take an algebraic variety, you take a G, an algebraic group acting on X, everything defined over fixed sigma. Okay. You take an element G in G of K, and you consider the equation X is in X, and sigma of X equals Gx. Now, it turns out that this equation, I mean, the solutions to these equations are internal to the fixed field. It's better seen when X is really G, for instance, and the action of G on G is just left translation. Then you see that if A and B satisfy the equation I wanted, then if you take A inverse B, it's going to be fixed by sigma, right? Because well, when you look at what it is, when sigma of A inverse B, this is going to be A inverse GB, so A inverse B. So it's fixed by sigma. In other words, the set of solution of the equation is just the right coset of A by the fixed of G. And you all know these kind of equations when G is GLN, right? Okay. So the things I define here, this is what's called translation varieties. And you would like to say that all the examples are like that, more or less. Well, this is not true. But sometimes it is true. So again, I have K algebraically closed, I have A, a finite tuple. I'm assuming, so not only A over K is fixed sigma internal, but actually K of A sigma, so the difference field generated by A over K, contains no new fixed element. So that's an important. And we are looking at the field L, which is generated over K inside U by the set Q of all realization of the quantifier free type of A over K in U. Okay? So in other words, they satisfy the difference field they generate over K is isomorphic to the one generated by A over K. And we look at G, which is the automorphism group of L over Kf, where F is fixed sigma. So L is a certain difference field extension of K, and one sees easily that it actually contains the fixed subfields of U. Okay? So I'm going to be interested in the automorphism of this difference field L, which fix Kf. Okay, if you think about Picard-Ratio theory, this is totally natural, except that in Picard-Ratio theory, your F is inside K. Right? And we want to describe this G. So, I guess before continuing, before saying that this is really interesting, I would like to say why we started looking at this. It's because it comes from a problem in algebraic dynamics. So what's an algebraic dynamics? It's you have an algebraic variety V, you have a dominant map phi from V to V, and you want to look at so that's an object, V phi. Okay. Then you have a notion of morphism between algebraic variety, which means that algebraic morphism between the underlying varieties and then which commute with the transition maps. Okay? This can be all, problems about these things can be translated into problems of difference fields, and so you can answer certain questions. So the questions you had was, it was a question of having a difference variety, so a V phi, an algebraic system defined over K prime, a large algebraically closed field K prime, for instance, the algebraic closure of C of t. Then another algebraic dynamics, W psi, defined over a smaller subfield, let's say C. And you know that the W psi, the algebraic dynamic, projects onto V phi. So what does it mean? It means that there is a dominant map from W to V, which commutes with where the various phi and psi commute, and H. Okay, whatever. Makes sense. So the question is, what can you say about V phi? And it turns out that if V phi is not internal to the fixed field, okay, so if the equations x is in V and sigma of x equals phi of x, if this equation is not internal to the fixed field, then actually your V phi has a proper quotient, V0, phi 0, which is defined over the smaller field, okay, over C. When the degree of phi is greater than 1, okay, so then there is a finite quotient which is defined over the smaller field. Good. But okay, what happens when degree of phi equals 1? What happens when your equation sigma of x equals phi of x is internal to the fixed field? What can you say? Well, it turns out, in order to do that, you need to understand what are the things which are internal to the fixed field. What does it mean to be internal to the fixed field? And that's how you obtain a generalization of this result to the case of things which are of degree 1 in particular. Okay? So this is the type of corollary we get. Let V phi be defined over C of t. Assume that for some m, if S denotes the set of points of V of C of t represented by rational functions of degree less than or equal to m, then for every n, the set of P and of n iterates of P under phi is Zariski dense in V. So this is sort of, think about it. You have your favorite point, you start applying phi. Now, if phi involves powers of t, chances are that the degree in t of phi of p is going to be much bigger than the degree of p, etc., etc. Right? So to say that it's bounded by an m, that you actually can have arbitrarily long strings which are bounded in size, then this is a very strong condition, and it actually says that, well, it's because V phi has a quotient which is defined over C. Okay. Right, so this is the kind of thing has a proper quotient. I mean, it's not a point, it's a variety of positive dimension. So in particular, if you are starting with a variety of dimension 1, you get something of dimension 1. Isomorphism. Okay, so I should say that you cannot hope to get isomorphism, that there are examples where in the internal case you do not have isomorphism. I'm not going to, I mean, maybe I'll get back to this if you want to, but let's proceed. So let's go back to the thing. So we had this example of translation varieties. We would like to show that it's all of them, that all the things which are internal to the fixed fields are actually of that form. So we have this A, such that A over K is fixed sigma internal. Remember that it means that there is over some larger difference field E. That means that E of A sigma is isomorphic to E of B, where B is a fixed field. And we look at the field generated by by the set Q of realization of the quantified free type of A over K, and we look at G, the Galois group of this, the automorphism group of this. So there are several things you can start to show. So the first thing is that because K is algebraically closed, you actually see that the difference field generated by A over K is finitely generated as a field. So that's well, because if you look at it over E, it's certainly finitely generated as a field. Okay, so therefore, replacing A by some A sigma of A and so on, you may assume that K of A sigma is really K of A. So that means that when you have an isomorphism between K of A sigma and K of A, that in a sense, when I'm talking about difference by rational maps, I'm actually talking about just ordinary birational maps, really, because the sigma is in there. Now, as with Picard-Vessieux extensions, if this L is not a regular extension of Fk, then in fact it means that L contains some new points of F-alge, of the algebraic closure of F. Then G has a subgroup of finite index.
What was F?
Well,
F
is fixed sigma. F is fixed sigma. Okay. Now, more important is that L is finitely generated over Fk. So that should remind you of fundamental systems of solutions, right? In the case of Picard-Vessieux. In the case of an equation of a linear equation of degree n, you need to have n solution to this thing, and then you get the whole thing. So here, same thing. And actually, right. So let's take the tuple B of realization. Now, there are many choices for B. But actually, if you take this B bar to be what I would call mutually independent realization of the quantified free type of A over K, chances are that when you look at K of the B bar, you're going to have it increased a lot, the fixed field. But, well, that's life. But, so this B bar, which is a fundamental system of solutions, so that means that if you take an element of the automorphism group, it will be completely determined by the image of B bar. Okay? Because if I look at row of B bar, it will also have the property. So what do we have? We have that L is equal to Fk of B bar. So it's also equal to Fk of row of B bar. Okay, so let's say this is some C bar. All right, now this C bar is what? This C bar, it's going to be, C bar is going to be of the form F of B bar, where F, no, I should write something else, sorry. Where F is just a polynomial, rational function rather, and B bar is a tuple in F. I'm not writing anything deep here. I mean, it's just I'm translating this equality. And you see that basically, I mean, if you choose well your D bar, well, actually it will be unique. So you can start fabricating functions which, to an element realizing the quantify-free type of B bar over K associates a tuple of elements in the fixed field and so on and so on. And, well, you can sort of interpret the group of automorphism of L over Fk with the help of this F, I mean, this defines a group generically, but then you use Bell's construction and you try not to get completely confused. And, well, you manage to get something. And you get, indeed, the quantify-free definable group G, which is isomorphic to your thing, to your automorphism group, which acts on Q on the left, and everything, the action and everything being defined over K. Q is the set of realization of my quantify-free type of it.
But you have to take into account these independent parameters that you have to...
No, I'm saying no. This requires some work. I mean, I'm getting a family of groups, okay? Up there, I'm getting a family of groups which is indexed by the B bar, okay? But I have isomorphism between those guys, okay? Which commute, everything commutes well. So now you have again, so you pass to the algebraic setting, and you have a theorem of Weil which tells you that you can sort of get something which is defined over K, because everything commutes. However, the thing that you get is not living inside fixed sigma, not like the other ones. Okay. And then you go to the opposite thing, so you get, in fact, a group, H bar, which is an algebraic group. You take the fixed point, and it acts on the right on Q. Okay, so I mean, you are now in a situation of a sort of we have two actions, one of them is opposite to the other one, and, well, the problem is that all these things are defined over a larger field, right? They are defined a priori over K of B bar. Actually, this H is defined over K of B bar intersect F, which is a bit smaller, but it might be still be bigger than my K intersect F. For instance, yeah, right. And okay, I guess I wanted also to say, so quantify-free type of A over K, what does it say? It says that A satisfies certain sigma equations, okay? But a priori it also says that it does not satisfy a lot of other sigma equations, okay? So it turns out that they are finitely, you need only to say finitely many inequations, which is non-trivial. Okay. Now, the problem is that, as I said, things were defined over K of B bar intersect F. So it would be, if we want to have, I wrote something very very difficult to prove. So if we if we want to have our H, I mean, if we want to find our translation variety, which is isomorphic, which is K isomorphic to our original problem, we need really that the fixed point of K of VB bar, they should be inside K. Well, they are obviously inside F, but they should also be inside K. Then you would get that the action would be defined over. You would get that the H bar would be defined over K intersect F, the action over K. So this is, then you would be close to get something. This is not possible all the time. It is possible in some cases. So one of the cases where F intersect K is pseudo-finite. So that means that actually it's an elementary substructure of the fixed field of U. And well, you have a model theoretic argument which says that you can descend the B bar. You can specialize it to something which is still a bunch of realization of the quantifier free type of A over K, which is still a fundamental system of solution, but does not increase the fixed field. Okay? Same thing when F intersect K is algebraically closed and L is a regular extension of Fk. Remember that if L is not a regular extension of Fk, this is because it contains elements which are in the algebraic closure of F, not in F. So it's going to contain elements, for instance, which satisfy sigma square x equals x, and sigma of x different from x. So these guys can certainly, you can certainly not specialize this situation to something which lives inside, where the fixed part lives inside an algebraically closed field, okay? So this requirement is necessary. It turns out that it's also sufficient. And, okay, so then we get exactly the, in the case of linear difference equation, we get exactly the Picard-Bessieux thing. So I was telling you things about, the fact that we assume that the difference field generated by A is over K is actually the field generated by A over K. So that means that instead of talking about difference rational maps, we can talk about rational maps. This also means that, when you go to the Zariski closure, if you have an action, well, this passes to an action on the algebraic varieties. And indeed, so we have this H bar, which, we had its H of F, which was acting on the set X of realization of the quantifier free type of a fundamental solution. Well, if you pass to the algebraic closure, you're going to get an algebraic group H, which acts on the Zariski closure of X. Moreover, it's really a torsor thing. H of F is really in bijection with X, right? So at the level of the algebraic level, it's the same thing. So you can, without loss of generality, assume that they are equal. As soon as you have a point of X, of K, you get an isomorphism between. As soon as you have a point of X bar of K, you get an isomorphism between X bar of K, between X bar and H bar, right? Right. And then from this, you show that X is actually the set of solution of, is actually a translation variety, okay? You get explicitly what it should be. And from the fact that this X is something, then you constitute by some stabilizer and you get the same result for Q. Okay, more or less. Okay. It might be, so my Q is going to be contained inside the Zariski, inside the translation variety. Okay, right. Now, what happens in the general case, right? I mean, this is just in the case when I can nicely specialize my fundamental solution to another fundamental solution which does not increase the fixed field. Well, in that case, that means that actually what you are doing is that instead of looking at sigma, you go to sigma n, sum n, and there it works. So in other words, instead of looking at Q, you look at its sigma n closure, so the things which satisfy the same sigma n equations as A does, well, this is going to be isomorphic to a sigma n translation variety over K. Okay. So it's not good, but it's not horrible. So this tells you what. So I guess I wanted to say now a few words. Arnold, in his talk, he mentioned trying to do this stuff on constrained cohomology to generalize it to difference fields. As you see, you have really lots of groups arising here. I mean, any algebraic group can arise, and any algebraic group is going to give rise to a internal, to something which is internal. So what do you do, really? I mean, it's. I mean, the notion of Liouville closed is going to be very big. That's what I'm saying. Okay, so let's go back. When do I have to finish? 55, so I have finished. So let's go back to the problem, right? So we have discovered that all our things are. Let's see what happens when actually. So we want to apply this to algebraic dynamics. Now, if you think about algebraic dynamics, how do you associate to an algebraic dynamic a difference field? Well, that's very easy. So you have, say, V phi defined over K. You look. Your V should be preferably irreducible. You look at the field of rational functions of V, and you define sigma to be phi star. So in other words, phi star of an element of F is just equal to, and I never know how it goes, F circle phi. Okay, so it's a map from V to K. This defines an endomorphism of the field K of V, which is an isomorphism if the degree of phi is 1, which otherwise it's not onto. But okay, it has. There is a. I mean, then you take the inversive closure, I believe. Right. So you notice also that the phi star is the identity over K. So in other words, I'm looking at an A. I'm looking at an A over a field which is fixed by sigma. Okay? Right. So assume now that my A and my K, I could have two. Okay, I wasn't sure. Assume now that my K is contained in F. I remind you it's algebraically closed, right? Now, what turns out is that the group G is abelian. It's commutative. So you just show it. It's fairly easy. It's because, I mean, by definition, the elements of G are things which commute with sigma. Okay? And, I mean, and you just get that it's abelian. And not only that, but it's generated by one solution. So actually, H bar and G, I mean, you know, you don't have op because it's abelian. Okay, so that's nice. So you apply it to the descent problem. So I have a small field which is C. I have a large field which is K. I have a variety. Remember, I had things. I have a V phi. Which is defined over C of T. I have a W psi which dominates it, but which is defined over C, small field. Now, by the results I was mentioning, this is going to be isomorphic to some abelian group A and some translation map. Okay? And this, well, maybe I shouldn't put A, I should put G. And this is going to be isomorphic to some B, and Y goes to Y plus B. Okay? And actually, if pi was the map from W to V, which made that everything commute, you will have, of course, what we call not B, H, pi of H equals G.
The isomorphisms are over C or over CT?
Well, obviously, they are over C of T.
But the P is not over
Okay,
C
this
anymore.
one is over C, this one is over C of T arch.
Okay.
And this is defined over C of T arch. Now, from this, you notice that if A is semi-abelian, then in fact B can also be chosen to be semi-abelian. And it turns out that because A has really very few isomorphisms, endomorphisms, that actually, well, the whole thing is going to descend to C. So A and phi is going to be isomorphic to something defined over a smaller field. So, remember what I wanted to show? I wanted to show that V phi has a quotient which is defined over the small field, right? That's what I want to show. Okay, so if my variety is semi-abelian, it's done. Not only it has a quotient, it itself is isomorphic to something defined over a small field. So if it has a quotient which is semi-abelian, it's going to be okay too, because that quotient is going to be isomorphic to something defined over the small field. So the only thing that remains is if A has no quotients which are semi-abelian, in other words, all its quotients are isomorphic to GA. We are working with GA, so we might as well. So anyway. So without loss of generality, it is GA. And then, well, you look at what the possibilities are. So either it's the identity, or it's going to be translation by a non-zero element, and translation by a non-zero element that you easily see that it's isomorphic to GA with x goes to x plus 1. So this is the end of the proof. And I guess this is the end of my talk, too.
So are there any questions? No, so let's thank Zoe and Dean and we start again at the